Welcome to this video on continuity and the precise epsilon delta definition of limits. These concepts form the foundation of calculus and help us understand when functions behave nicely versus when they have sudden jumps or breaks. In this video, we'll cover four main topics. First, the precise epsilon delta definition of a limit. Second, how to apply this definition in examples. Third, the definition of continuity at a point. And finally, examples of continuous and discontinuous functions. Before diving into the precise definition, let's understand limits intuitively. Consider a function f of x. The limit of f of x as x approaches a equals L means that as x gets closer and closer to a, the function values f of x get closer and closer to L. Importantly, the limit is about the behavior of the function near the point a, not at the point itself. We are looking at what happens as x approaches, but x is not equal to a. Now, let's formalize this intuition with the epsilon delta definition. We say the limit of f of x as x approaches a equals L if, for every positive real number epsilon, there exists a positive real number delta, such that if the distance between x and is less than delta, but x is not equal to a, then the distance between f of x and L is less than epsilon. In this definition, epsilon measures how close f of x must be to L, while delta measures how close x must be to a. Let's work through an example to see how we apply this definition in practice. We'll show that the limit of 3x plus 1 as x approaches 2 equals 7. According to the epsilon delta definition, we need to show that for every positive epsilon, there exists a positive delta, such that if the absolute value of x minus 2 is less than delta, then the absolute value of 3x plus 1 minus 7 is less than epsilon. Step 1. Let's simplify the expression inside the second absolute value. 3x plus 1 minus 7 equals 3x minus 6, which equals 3 times x minus 2. Step 2. So, the absolute value of 3x plus 1 minus 7 equals 3 times the absolute value of x minus 2. Step 3. To ensure this is less than epsilon, we need 3 times the absolute value of x minus 2 to be less than epsilon. Solving for the absolute value of x minus 2, we get that it must be less than epsilon divided by 3. Step 4. Therefore, we can choose delta to be epsilon divided by 3. With this choice, whenever the absolute value of x minus 2 is less than delta, the absolute value of 3x plus 1 minus 7 will be less than epsilon, confirming our limit. Let's visualize this example. Here's the graph of y equals 3x plus 1. The point 2, 7 is highlighted, which is where we're finding the limit. If we choose an epsilon, say 0.6, then the corresponding delta would be epsilon divided by 3, which is 0.2. We can verify that for any x within delta of 2, so between 1.8 and 2.2, the function value f of x is within epsilon of 7, so between 6.4 and 7.6. Now that we understand limits, let's define continuity. A function f is continuous at x equals a if, and only if 3 conditions are met. First, f of r is defined. Second, the limit of f of x as x approaches a exists. And third, the limit equals the function value at a. Equivalently, using the epsilon delta definition, a function is continuous at x equals a if for every positive epsilon, there exists a positive delta, such that whenever the absolute value of x minus is less than delta, the absolute value of f of x minus f of a is less than epsilon. Let's look at examples of continuous and discontinuous functions. First, a continuous example. F of x equals x squared is continuous at x equals 3. Let's check. F of 3 equals 9, so f is defined at x equals 3. The limit of x squared as x approaches 3 is 9. This limit equals f of 3, which is 9. Visually, there's no hole, jump, or break in the graph at x equals 3. The function value matches the limit value, and the graph is unbroken. Now, let's look at a discontinuous function. Consider g of x equals x squared for x not equal to 2, and g of 2 equals 5. Let's check continuity at x equals 2. G of 2 equals 5, so g is defined at x equals 2. The limit of g of x as x approaches 2 is 4, because for x not equal to 2, g of x equals x squared, and the limit of x squared as x approaches 2 is 4. But g of 2 equals 5, which is not equal to the limit. Visually, There's a hole in the graph at x equals 2 with the function value at a different point than where the rest of the function approaches. Let's look at another type of discontinuity, a jump discontinuity. Consider the function h of x equals 1 for x less than 0, and h of x equals 2 for x greater than or equal to 0. In this case, h of 0 equals 2, so the function is defined at x equals 0. However, the left-hand limit as x approaches 0 from the left is 1, while the right-hand limit as x approaches 0 from the right is 2. Since these one-sided limits are different, the overall limit doesn't exist at x equals 0. Visually, this creates a jump in the graph at x equals 0, where the function suddenly changes value without a smooth transition. Let's summarize what we've learned. The epsilon delta definition of limits formalizes the intuitive idea that a function approaches a certain value as the input approaches a certain point. Continuity at a point means that the function is defined at that point, the limit exists at that point, and the limit equals the function value. Discontinuities occur when any of these conditions fail. Either the function is not defined, the limit doesn't exist, or the limit doesn't match the function value. These concepts are fundamental to calculus and form the basis for more advanced topics like differentiation and integration. Understanding them gives us a precise language to describe function behavior and analyze mathematical models of real-world phenomena. Thank you for watching. I hope you now have a clear understanding of continuity and the precise definition of limits. These concepts might seem abstract at first, but they are essential tools that allow us to develop the powerful methods of calculus.